3 is about linear systems, and where we're talking about systems of equations, where you could have 2 or more equations that include 2 or more variables. So we're actually only going to do the first 3 lessons in this chapter, but I am going to provide one of them. I think it's lesson 5 or 6. I'm going to give you some chance to do some extra credit if you're willing to take on that task. So a linear system is a system of equations containing only linear equations. So we could look at these two together. If I had those 2 equations together, 3 and 4 there, we could call that a linear system. All right? And there are a couple different things that can happen with that linear system. We can have 2 lines that cross, so we have one intersection point. Or we could have the 2 lines be on top of each other, where then there would be an infinite number of solutions. Or we could have 2 parallel lines where there's no solution. And we're going to look at each of those situations in this lesson. So first of all, we want to verify whether this point is a part of the solution. So what do you think we would do to tell whether the point 1, 3 here, whether it's a solution to this system of equations or not? What would we do? Spencer? We could do that, okay, and then graph it and see if it worked. Okay, that's one thing we could do, and we're actually going to do that with graphing in a little bit. Anybody with another idea? Okay, plug them in, okay? Let's put them in for x and y and see what you get. All right, so we'll take each equation and put 1 in for x and 3 in for y. So we'll try the first one. 1 minus 3 times 3 equals negative 8. Okay, is that true? 1 minus 9 equals negative 8. All right, so that works. Okay, so it works for that one. 3 times 1 plus 2 times 3, does that equal 9? So 3 plus 6 is 9, so they're equal, so yes. So is the point 1, 3 a solution? And the answer is yes. Okay. All right, so try it for B then. Make that one quick. Okay, this one's not going to, so we put negative 4 in for x and 1/2 in for y. So here we're going to get 2 equals 2. Okay, that one worked. 2 times negative 4 plus 8 times 1/2. Does that equal 1? And negative 8 plus 4 is negative 4, which is not equal to 1. Okay. So no for this one. All right. Okay. Good. All right. So now we're going to look at using tables and graphs to solve them. Now the thing is that when we make graphs here, you have to have them exact. So that means that you're going to have to use graph paper, and you're going to have to make sure all your stuff is exact. Otherwise, the points you get will not work. So you need to make sure you're doing it correctly. All right, so first thing we have to do is we need to get them in slope-intercept form, or you could just find the intercepts if you wanted to. Now, I want to put it in slope-intercept form because when we get to example 3, we're going to be using that anyway, so we need to do some more practice with it. So the first one, 2x minus 3y equals 3. I'm going to solve that for y. So I'm actually going to add 3y to both sides first. All right, just so my y is positive. Does it matter? No, not really. Subtract 3. and then divide. So we get y equals 2/3 x minus 1 would be this line. Okay. Oops. All right, now, and let's do the other one. The other one we're going to subtract 2, so we get y equals x minus 2. So we got y equals 2/3 x minus 1, so we'll graph that line on our graph paper, and that's why you have a ruler and graph paper, so your graphs are accurate. And what we're looking for is, where do they intersect at? Okay. So go ahead and draw these on your paper. So we've got the y-intercept. Graph that first. Make sure you're using graph paper. Okay? All right? If you use line paper, your intervals are not going to be the same and it won't be accurate. So you need to have graph paper, something where you can actually see intersection points. So for the first one, we had a y-intercept of -1 and a slope of 2/3. So I'm going to go up 2 and over 3 and then draw my line. All right, and then graph y equals x minus 2. And then we're looking for, where do those two lines intersect? And hopefully yours intersect the same place that mine does. So the answer to this equation, or to this problem then, is the point 3, 1. My answer is the coordinate where the two lines intersect. Okay, so that's what I'm looking for. Where do they intersect? All right, let's look at letter B. Here we have the two lines, x minus y equals 2, and 2y minus 3x equals -1. So we want to solve them both for y first of all. So we'll take the first one. We subtract x.
It works for me. We'll have to see if it works when you log in.
All right, I'll let you know. Thank you. And then we're going to divide or multiply by -1. So y equals x minus 2. Then take the other line and solve that for y. So we add 3x and then divide by 2. We get y equals 3/2 x minus 1/2. Said that it's important that you're able to solve for y to make your graphing easier, or you can use the intercepts. It really doesn't matter in this case which way you use to do it. It's up to you. It's personal preference. So then I'm going to graph the lines. For y equals x minus 2, we have a y-intercept at -2. Slope of 1, so we go up 1 and over 1. And then for the other one, I would draw it on here, but it's a lot harder. I don't have a ruler, so if I can get it to recognize, which it didn't, come on. If I can get it to recognize my work, then it's a whole lot easier. Oops, let's use this. Oh, there we go. Okay. And then we can see that these two lines intersect where? Okay. All right. They intersect down here at -3, -5, so that would be my answer. Okay, so I'm graphing the lines and then finding where they intersect. And then that's my solution. All right, so John put it in his y equals. So you've got, okay, y equals 4x minus 3. Okay, and then the other one you did what? Okay, so I can put that in parentheses. X minus 6 divided by 2. That right there? Okay. And then if I hit graph, then I can actually see where they intersect there also. And if you go to your table, we can see that at 0, they both equal -3. Okay, good. You can do that also. All right? But you can look at your graph then, and I can estimate, it looks like where they are also. Okay, and you can actually, there is a way, if you hit second trace and then go to number 5, which is intersect, it will actually find it for you. It will tell you where the intersection is. So you can do that also. All right, but I'm going to expect to be able to see the graph. Okay. Nope, it will show any of them you want. Okay. All right, last thing then. Identifying systems or classifying systems. So a system of equations is an example to have exactly one solution. However, linear systems may also have infinitely many solutions or no solutions. A consistent system is a set of equations or inequalities that has at least one solution, and an inconsistent system has no solutions. You can classify linear systems by comparing the slopes and y-intercepts. That's why it's important to be able to write them in slope-intercept form. An independent system has equations with different slopes. A dependent system has equations with equal slopes and equal y-intercepts. Well, if it has an equal slope and equal y-intercept, what is that? Okay. It's the same line. Okay. So a dependent system is actually going to have the same line. So here we go. We've got, if they're consistent and independent, consistent and independent means that there's one that they have different slopes, different y-intercepts, or different slopes, I should say. If they have the same slope and the same y-intercept, they are consistent and dependent. And if they have the same slope but different y-intercepts, then they're inconsistent. So consistent and independent, one solution. Infinite many solutions, then they're consistent and dependent. And if there's no solution, then they're inconsistent. All right, so what we're going to do is we're going to classify these linear systems, but to be able to do that, you got to put them in slope-intercept form. And then we'll just see, what do they have? Okay? How do their slopes compare? How do their y-intercepts compare? Okay. So letter A, we're going to solve for y. So the first line, we will subtract 6, so we get x minus 6 equals 2y. Then divide by 2. Now, you have to make sure that you simplify this. So a reminder, this is 1x. So it's going to be 1/2 x minus 3. Okay, we're dividing both parts by 2. Okay, with the second equation, we'll subtract 3x, so we get negative 6y equals negative 3x plus 18.
I'd like to have your attention. It is time to release the JV softball and baseball players.
Okay, so then we'll divide by negative 6. We get y equals negative 3 divided by negative 6. That'd be positive 1/2 x. And 18 divided by negative 6 is negative 3. So I compare my y-intercepts and my slopes. So in this case, the y-intercepts and the slopes are the same, which means then it's the same line, right? So if it's the same line, then it says classify and determine the number of solutions. So we have this one right here in the middle. So I'm going to say it's a consistent and dependent, and there are infinitely many solutions. Consistent and dependent and infinitely many solutions. Let's look at B. So once again, we're solving for y. So in the first one, we'll subtract 4x. So we get y equals negative 4x plus 1. And second one, we'll subtract 1. So we get y equals negative 4x minus 1. So here we have the same slope, but different y-intercepts. Tells you that the lines are what? Parallel. Okay? They're parallel lines, which means then that they are going to be inconsistent, and there is no solution. Same slope, okay, different y-intercept. Okay, so we would have, let's see how good I did this time. So even though it changed my y-axis, you can see they're parallel. So there's no solution there. Okay? All right, questions about these? So with these then, you're going to have to get them into slope-intercept form. Just compare the slopes and the y-intercepts to be able to classify. Now if the slopes are different, then it's consistent and independent, and there's one solution.